All right, so stretching period is over. Okay. Okay, so in this last lecture then, I'm going to talk about brain. I have a little bit of background, though, that I want to go over first in terms of mainly what is diffuse correlation spectroscopy in a little bit more detail. And then I want to talk a little bit about metabolism and autoregulation before I start showing you examples. Okay, but then the last part is, again, really translation to the clinic. Okay, so first, just to say one thing is that for looking at the brain, again, a lot of people in this audience know this already, but there is really an opportunity. And there's really an opportunity because if you look at what people are using now, there are serious limitations. So one of the limitations is that a lot of the devices, and these are devices that my colleagues in the medical school use, they literally are drilling a hole in the brain and sticking a needle into the brain, okay? Then they can measure something that's useful, like the oxygen tension or the pressure or something like that. But still, they could also induce a stroke, a bleed by doing that, okay? So it's not, so there's an opportunity for optics if we can show that we can measure stuff that gives you the same information or even complementary information is useful, okay? About, things like oxygenation and metabolism and so on. So there's an opportunity from that point of view. And then even if you look at some of the other non-invasive techniques, like MRI or xenon CT, these are basically techniques like, again, with the MRI, you're just mainly, if you had a patient that's got a brain injury and they're going into the neuro ICU, they're not going to, they may measure it once, but they're not going to be measuring it every day. Okay, it's just a low throughput technique, it's expensive. And so we have this opportunity again with optics that we're a continuous bedside instrument, okay? And so if you want to have sort of an individualized patient management at the bedside, then optics is a good possibility. And the challenge for us is to show that we can have value in that, okay? So I'm just flashing this up again, and I talked about some things to do with breast cancer. Now I'll talk about, the kinds of clinical questions you can ask. There are lots of things that you can just think about in terms of managing brain injury, okay, for stroke, trauma, different kinds of trauma, all sorts of things like that. And managing, you want to detect things, diagnose things, monitor therapy, even induce therapy, you can optically do stuff like that. In terms of understanding how the brain works, there's actually a lot of interesting excitement. Maybe Rickson will talk about it, but basically looking at networks in brain activation. These tools that I'm telling you about are useful for that. There's other things that I didn't talk about that are also useful for this. Okay, so let me first then tell you a little bit about, I want to tell you about three things before I show examples. I want to tell you mostly about flow, and then I'll tell you a little bit about metabolism and autoregulation. Okay, so blood flow, I've already talked a little bit about one technique in the single scattering limit called dynamic light scattering, remember? And so in that case, instead of looking at the average value of the phase or the amplitude of your light wave, diffusive light wave, you're looking at the fluctuations of the signal. And they're rapid, they're microsecond, nanosecond, millisecond. They're rapid. And so that information is there. And basically that information, as you may recall, in the single scattering case, had to do with particles diffusing. And so it has to do with stuff moving, okay? And the most important thing that moves is blood, and these problems that I'll talk about. And so there's information about that's on this diffusing light signal, okay? So just to remind you, this is a slightly different slide, but if in single scattering, I do a standard measurement is you have some cuvette filled with particles that are fairly dilute. You have a detector off at some angle. You measure this autocorrelation function, either the field correlation function or the intensity autocorrelation function. I'm plotting the log of it here versus time. And the slopes of these basically tell you how fast stuff is moving. In this particular case, at the two different temperatures, the particles change their diameter. And so the ones that are smaller are moving faster. And that's why this one will decay faster than this one, okay? And so, again, just to remind you, the most important part about this signal, this autocorrelation function, is that it depends on the mean square displacement of the particles. In the case of this example that I've given you, it's just diffusion. Okay, so delta R squared, I can replace it by d, the diffusion coefficient of the particles, times tau. That's from Einstein. Okay? So what we wanted to do is to extend this to turbid media and to extend it to tissues. Okay? And so you'll be hearing from David next week. So David, he was my grad student. And basically, he thought about this problem and made a lot of progress about it. And the way to think about it is not very dissimilar to what I told you before. Okay, so if we had tau equal, this is the correlation function of the electric field. If tau equals 0, it's just the fluence rate. Okay? And so before, we thought of the fluence rate as having sort of a set of n independent single scattering events in going from the input to the output. Well, it turns out that you can think of the same thing as happening for the correlation. Now, in the case of the fluence rate, you could lose light fluence, light energy, because of absorption. In the case of the correlation function, you also can lose due to absorption, but you can lose also due to motion. Okay? And so basically, before David started working on this, there was some work where people looked at the transport of correlation, and they wanted to understand what happened really with only a couple of scattering events. And basically, they wrote down a transport equation for the correlation function. And David basically just, we were all familiar about what we did for the diffusion equation. He just did the same thing for the correlation transport, okay? And basically, at the end of the day, we got a diffusion equation for correlation. Okay, so G1 is that E star T plus tau times E, okay? And the only thing that's different from before, the D here is the diffusion constant for light. The mu A is the same absorption, but you have an additional absorption term that's due to the motion of the particles. And it's multiplied by this scattering factor, it's multiplied by this term alpha here is sort of the fraction of the particles that you scatter from that are moving. So it depends on that too. But anyway, it's a very well-defined additional absorption, and you can and what this allowed us to do is we can solve this in the same exact way that we solved our diffusion equation for the fluence rate. But we're just looking at a different measurement variable. So instead of looking at phase and amplitude of the diffusive wave, we're looking at this autocorrelation function, okay? But the decay rate of this autocorrelation function in time tells us about the motion, and I'm going to sort of call this combination the blood flow index, okay? So let me just try to drive this home. Here's an experiment by Chao Zhou some years ago where we put basically a probe on the head of a pig, and we were interested, actually Susan Margolis was my collaborator, and she was interested about understanding traumatic brain injury for babies, actually. And so she had a way to cause an injury in the pig by just moving the head really fast. But anyway, all I want to point out is this is the correlation function that we measured when the pig was living. And this is what it was when it was dead. So this is there's many ways to tell that something is living and dead. This is not one that I would recommend, okay? But the main thing I want to show you is that it's a factor of 100 difference in the decay rate. This is a log scale. So this is a very big change, okay? And, in general, we're going to be looking at much smaller changes, 10%, 15%, 50%. But you can measure them really well with this technique, and you're basically measuring this decay rate, okay? Here's a measurement David did early on, just the basic cuff ischemia measurement, right? So he's basically cuffing his arm, and then we put the probe right here on the forearm, and the only thing I wanted to show you, this is the correlation functions that we measured, and when there's no pressure, it decays fastest. As we increase the pressure, it decays slower and slower. And you can do an ischemia measurement versus of this, all right? And essentially, the bottom line then, as I'm going to go forward, is I want you to appreciate that we're going to measure essentially these intensity fluctuations in time. And again, Valerie talked about doing speckle. You can do it other ways. And this is the best way, I think, for deep tissues, because it's the most sensitive way. But basically, I'm going to measure essentially some decay rate that I'm going to call the blood flow index, or F. And a lot of times, I'm going to put an R in front of the F when I'm looking at relative changes in the flow index, okay? And so if you see an RBFI, that means it's the change with respect to some baseline of the flow. But it's all basically measuring the decay in this decay time, okay, this typical decay time or decay rate. So I showed you this before, but I want to now say that I want to point out that by doing both the spectroscopy with the diffusive waves and this flow measurements with these diffuse correlation spectroscopy, we can really get a lot more information about the hemodynamics, okay? Because usually you can explain changes from this. If you just measure oxygen saturation, for example, you can explain it due to changes in flow or due to changes in metabolism. It's not unique. By measuring the flow also, you can sort of eliminate that uncertainty. Okay? So that's what we're going to do. And now I just want to give you one more piece of background about metabolism, two more pieces of background, about metabolism, oxygen metabolism, and about autoregulation. So again, oxygen metabolism, the beauty now is I can use all optical techniques, complementary optical techniques, to measure metabolism. And so just to give you a flavor about that, right? So imagine that you have, shoot, the T should be there. This is tissue here, okay? And so basically, this is very conceptual, but basically I have oxygen flowing in from the arterial side, right? So it depends on the arterial oxygen saturation times the flow rate, the amount that goes into the tissue. Then my tissue does work, okay? So that's the metabolism. And then the leftover oxygen comes out the venous side, and there'll be a venous oxygen saturation and a blood flow. So this work is related to the difference, right? And if I sort of take that and I make a little assumption, okay, about how the vasculature is partitioned into venial, what fraction of it is venous compared to arterial, okay? That's what the gamma is doing. And I assume that the oxygen arterial saturation is 1, which you don't have to do. Then you can show that you can rearrange this, and this oxygen metabolism, and I'm going to put a C here because we're only going to be concerned with cerebral oxygen metabolism, but you could have also looked at it in a tumor. This will basically depend on stuff we can measure. It's going to depend on the blood flow, which I can measure with the correlation spectroscopy. It's going to depend on the oxygen saturation, which I can measure with the regular diffuse optical spectroscopy, the monitoring technique. So this last lecture is only about monitoring, not about imaging. And so the gamma is a constant, which is an assumption. And I'm also assuming generally that it's staying constant. That may not be right, okay? So if you want to measure absolute metabolism, it's harder, okay? But we're not giving up about that. On the other hand, if you just want to measure the changes in it, then it's easy, because you just measure the changes in these variables. The gamma divides out, okay? So, Joe Culver did this first in an animal model a while back, where we looked, again, at the brain of a rat during, we looked at it in a lot of different situations, but one is we looked at it with breathing different gases. So you can have hypercapnia, hypoxia, and we can induce ischemia. And the main thing I want to point out with this graph is that sometimes the flow and the oxygenation change in the same direction, sometimes they're different directions. And that's useful, okay? It's useful to understand what's happening in the rat. And then Turgut showed a little bit later that you can do this measurement through the human skull. So again, he made a little probe. So we have a source and detector about 3 centimeters apart, so it's going to penetrate into the cortical region. And then basically we did finger tapping. It's a standard perturbation. And so if I finger tap like this, then my motor cortex over here lights up. If I finger tap with this, my motor cortex over here lights up. And you can measure all of these things: total hemoglobin saturation, concentration, oxygen saturation, relative blood flow. You can combine them to measure oxygen metabolism changes. And this is sort of a summary of that first experiment, where you can see this is the period when there's before the tapping, this is after the tapping, this is during the tapping. This is the results for 5 subjects, not patients. And you can see the flow going up. That's the blue curve during the activation part. You can see the oxyhemoglobin going up. You can see the deoxy going down. You can combine them to look at the average change in the metabolism. You can get a number. Okay, you can be very quantitative about the change due to this tapping. If you moved it to the wrong spot, if you moved this probe by 1 centimeter, you would get nothing. It would be flat. Okay, that's in the paper if you want to look at that. So hopefully this is just convincing you that we can get access to this the oxygen metabolism in the brain, which then can have value in managing brain-injured patients, for example. So then the other thing I wanted to mention was autoregulation. And so let me just tell you a tiny bit of conventional wisdom about it, which you could question, okay? But basically, for a healthy person, okay, when you stand up or you run around or when you do things, essentially your flow stays roughly the same, okay? So if I changed your pressure, that's driving, autoregulation basically means if I'm changing the pressure, so CPP is cerebral perfusion pressure. That's the difference between mean arterial pressure and what's called intracranial pressure, okay? This is driving the flow in your brain, okay? And there's a large range of pressures for which it could change, but even if it changes, your flow remains constant because your arterioles dilate or contract, okay? And so there's this famous picture that maybe some of you have seen, which is plotting the cerebral blood flow versus the cerebral perfusion pressure, okay? And so there's this big region here where it's normal autoregulation, where the flow is clamped, even though the pressure could be changing for lots of different reasons. And so, but if it's if the pressure is too low, then this can't change. And so when the pressure changes, the flow changes. And if it's too high, then it can't change also. It's maximally constricted. And then also, again, the flow will follow the pressure. So loosely speaking then, if you make a measurement of flow and pressure, and if flow is following pressure, that could be a sign that something is wrong. Okay? But if it's not following it, then that could be a sign that something is good. Now, before I go on, I'll talk about that later. I just want to make one caveat, and that is that many people hate this picture. People have come up to me after conferences and been angry at me for showing it. But basically, so there's people that have written other papers, and you can read there's a literature about it. But mainly, there's still a narrow autoregulation region where it maybe doesn't change very much, and it changes a lot more in other regions or something. Okay, all right. So I still want you to think about it the way I told you at the first. If your flow is following your pressure, that's a bad sign. Okay, if it's not, it's a good sign. Okay, so now what I wanted to do mostly, and we'll see how far we get, I just wanted to give you some case studies that we've been doing, okay? And this is like very much of a team effort. And I want to especially acknowledge Andy Kofke and Ram Balu, who are the doctors we collaborate with, but then Wes, Leanne, Lynn, Carla have done all this work, okay? So here's our setup. We got the optical stuff over here. This is our rack. And this is the environment that we have to work, so it's not that easy, actually. Okay, so my collaborators, they already do some of these invasive techniques that I told you about. And so again, somebody comes in, they're injured, they may do something, then they go to this neuro ICU, and they could be sitting there for several days, and they're giving different treatments to try to bring them back to health. And actually, really, one of the things they want to preserve as much tissue in the brain as you can. And so they almost always, these patients have this bolt and this drilled hole in the brain and needles stuck in them to measure this intracranial pressure, the ICP. They can measure also the oxygen tension, And even there's devices that measure white matter blood flow, although I will tell you that they're not very reliable. And then, of course, they measure other stuff. They measure the pulse rates. They measure the mean arterial pressure. I mean, if you measure mean arterial pressure and you measure ICP, in principle, you can get the CPP, okay? And so what we did is we wanted to just basically let them keep doing that and making whatever conclusions they're going to make based on their invasive probes. But then at the same time, on the forehead, just measure these things that we can measure, the flow and the oxygenation from which we can extract information about metabolism and so on. And, you know, we did this typically for patients. They would be there for many days. And again, we're using this bedside instrument, and so we're monitoring it continuously. And it's sort of fun working with the doctors later. You know, it's almost always retrospectively at this stage. And we're looking at all the different things that they're keeping track of, and then looking at our measurements and trying to make sense of it. And, you know, and so the kinds of things that we are sort of focused on then are adverse clinical events that occur during these treatments. And they could be, for example, spikes in metabolisms due to mismatches between the oxygen delivery and consumption. It could be this autoregulation being impaired. And I'm just going to show you a couple examples. Okay, so one, again, just to remind you, we can measure essentially, so we have the flow and the arterial concentration of oxygen coming into the tissue. There's work done, that's cerebral oxygen metabolism. There's flow out. And so this CMRO2, if you like, is related to the flow that I measure with DCS, and what's called the oxygen extraction fraction, which is essentially just 1 minus the blood oxygen saturation, okay? But people use this more, okay? And so we measure these two things. In this case, I showed you frequency domain measurements for most of the day yesterday. We actually are using time domain in this case in our instrument, but it's the same idea. And then what we did to look for, we were going to look for cerebral autoregulation, and then we can look for metabolism, both, by measuring these. So let me show you something about metabolism. Okay, so this was an anaerobic event in a patient with hemorrhage, and you know, basically, so this is what I'm plotting here is the flow compared to the baseline value, the oxygen extraction fraction, or blood oxygen saturation, 1 minus the blood oxygen saturation compared to baseline, the mean arterial pressure, and then this oxygen electrode oxygen. So that's tissue PO2 and the white matter at 1 point. And so you can notice that there was a big increase in pressure here, and they didn't know why, and so they just gave it phenylephrine, okay, to reduce the hemorrhage risk, because they don't want to have a high pressure, because they could induce a hemorrhage. And so then the pressure started coming down. But remember, we're measuring all these variables at the same time. So you'll notice, first of all, that these purple shaded regions, so at those times, those are 6-minute time intervals, I'm basically comparing, I'm going to measure what's the CBF compared to baseline, what's the oxygen extraction fraction compared to baseline, what's the metabolism compared to baseline. So that's what I'm showing here on the left. So this is all in relative units. And so you can see the metabolism goes up a lot, and then it comes down kind of slowly. And so this worked, this treatment. You can see the flow went up, and it came down faster. So there was a mismatch here between the oxygen metabolism and the flow, okay? And then you can see the oxygen extraction fraction, which went up when there's this mismatch, okay? So you can really map out that what's happening, right, in terms of the metabolism using these kinds of tools. Here's another event called an autonomic storming event. This is kind of like a seizure, okay? And so, again, if you have it, it's bad because it can make your brain likely to have other kinds of injuries. And so they try to get to lower the metabolism when this happens, okay? Again, you can see it. Here is the event. So you could just see from our thing that the flow goes up like crazy, the oxygen extraction fraction goes up like crazy. And so if you plot, and then they gave it gabapentin, which is a drug that is used to treat seizures, and they tried to get it to come back down, which it did eventually. I should point out, this is hours, okay, on these axes. And so again, you can see that there's a big mismatch between, they follow the same trends, but there's a big metabolism change. And so there's an elevated oxidative metabolism that you can detect. Okay, so those are two metabolism examples. Then let me give you a little bit about autoregulation, just a couple things. So again, just to remind you, right, this is the sort of autoregulation, it's the conventional wisdom. And so what we can do easily is to look at the flow versus changes in MAP. Now that's not perfect. It's really better if it's MAP minus ICP. And sometimes you can do that. Okay. So what we did, what I'm going to just show you is basically we made measurements over this time of a patient, okay, which had a traumatic brain injury where the pressure was changing kind of a lot. And we just looked at how does the flow correlate with changes in the MAP. And what you find, if you look at the correlation, is it's not correlated, okay? So in a way, what does that mean? It means it's good. It means it's autoregulating, right? At least the pressure changed a lot, and it didn't change the flow. Here was a patient where a different situation with this hemorrhage, and we were giving it drugs during this whole time. But basically, the main thing is we just did the same thing. We looked at the changes in the pressure and the changes in the flow. And what you find, if you look at all our data over this time period, is just that it's basically it's changing. So the flow is changing with mean arterial pressure. And so here you would say it's not autoregulating, okay? And so we think that this kind of thing is a useful tool. And in fact, in this case, in these two cases, it was consistent sort of with what happened later to these patients. Okay, so that's some case examples. I'm going to sort of now switch gears a little bit. I want to talk about sort of things that where we can have improvement. Okay, because we also, part of what I like to do is to make technologies that work better for these things. And so one thing that we try to do is to calibrate. So you'll notice that we're very good at measuring relative changes, but we're not actually that good, and it would be desirable to be better at measuring absolute flow. So we have to figure out ways that we can try to calibrate that. And so I'll tell you about a study that we did recently in these injured patients, okay, where we basically tried to calibrate the DCS, okay, so this autocorrelation measurement with a bolus of ICG again, okay, that's the one that's allowed, okay. And so basically what we did is we have a patient, and again, we're monitoring it for hours, this patient. And basically, we give a bolus. If you give a short bolus, then you can measure the uptake. And you can analyze that curve of the uptake if you know the impulse response function, which you can measure also. And then from that, you can extract what the flow is in the tissue. And so I won't go into the detail of about this, except to say that what we measure is, with this time-resolved technique, is we measure sort of the change in the absorption due to the ICG, okay? So in this case, of course, ICG absorbs and fluoresces. So here we just measure the change in the absorption due to ICG coming in and then going out. And that curve, when you deconvolute it, can give rise, you can determine the flow. So you have to take my word for it. Here's one of the papers on it. There's lots of papers. Adam Liebert wrote a lot of papers about this. So anyway, the main thing is this is a way to absolutely get the CBF, okay? And so what we did is we measured, so here's a trace of a patient, all right, on different days, actually. And so we just measured, for example, we did the ICG measurement, and we measured the flow at that point. The blue point is the ICG measurement, and we measured the decay rate of our autocorrelation function at that same time. Now then we can continuously measure with the DCS, for hours. Now you're not going to keep doing bolus, okay? So the idea was that we could do the bolus once and then have the calibration for the rest of the time. So what we did, though, for this particular experiment is we just then measured it 4 hours later. Okay, and we just compared, is the calibration here the same as the calibration here? Okay, and so the calibration is basically the ratio of the cerebral blood flow that I would measure with ICG bolus divided by my blood flow index from DCS. And so here's just a plot of gamma 1 versus gamma 2 for the patients. You know, it's nice and linear. It's pretty good, actually. If you look really carefully at the fluctuations, we're still not that good. I'd like to do better. There are a lot of reasons that I think we could do better. But, you know, basically, if you want to just get within like 30% of an absolute value, you can just take this this calibration and then apply it to the decay rate, okay? And so I just want to, so this is something that still we're trying to do it better, but the value of it is that then a lot of times you care about what is the absolute flow. And so this will give you a way to do that with DCS. But even still, if you just make a measurement of, if you just do a calibration measurement during the beginning of the treatment, it probably is going to stay good for the rest of the treatment. So you can have how the change of that is going. Okay. So, okay, good. So now I thought I would tell a little bit about some other technical advances, okay? And so one problem that I've mentioned but kind of glossed over is how do we, so, you know, the brain at the very minimum, you can think of it as two regions in these measurements like this, right? There's the extracerebral region, which really is not just one medium, it's a scalp and a skull. And then there's the cerebral tissue, which you care about. And so really, we want to, if we can, separate the flow signal from the cerebral tissue compared to the extracerebral tissue. And it turns out that you could make progress on this problem, especially if you are only concerned about flow changes rather than absolute, okay? And so, so here, okay, this may look painful, but you remember I told you about the modified Beer-Lambert law yesterday? So this was a way that with the regular spectroscopy, I could measure, by measuring the optical density change, so the intensity change, comparing a baseline to some perturbed period, I could relate that change explicitly to the change in the absorption, okay? This is the same thing, except that I'm going to use the flow signal. So I get a decay rate, say this is initially, this one here, then it changes due to some activation, maybe my finger tapping. And so I get a curve like this, and then for any given tau, there's actually a lot more information, but for any given tau, there's a change in the optical density of the ECS flow signal, okay? So you can just do the same analysis, pretty similar analysis, and you can show that you can measure, if you make this measurement, you can relate it explicitly to the change in the flow. There's some, again, before, remember we had this average length travel of distance in the brain traveled by light. Now we have another parameter related to that, okay? But again, something that you can calculate. So so this is good. Again, this is good for semi-infinite media, but we want to look at least two-layer media, okay, right? So the way that we do this is, again, we follow ideas that have been out there in NIRS community, in DAS and NIRS community. And so we have two separations, one short separation and one long separation. So the short separation just probes in the overlayer, the extracerebral tissue. The long separation probes in the deeper tissue, okay? And so again, loosely speaking, you can just think, well, I should just subtract the flow signal from this total, because this big one, this large separation one goes through the extracerebral tissue. And that's, you know, that's not a terrible approximation, but you can do a lot better. And so we did do a little bit of work to do it better. And so the main thing I want to say is that we can use the changes we can relate the changes in the flow in the cerebral tissue to the measurements of the changes in the OD for the flow signal at the short distance and the long distance. And they're just a bunch of different parameters that multiply these things that we have to determine. So actually, you could say, well, you could calculate these. That's less desirable than figuring out what they are. But it turns out that you can figure out what they are by a simple measurement. Okay, and that measurement is to change the pressure of the probe. Because when you change the pressure of the probe, then you only affect the extracerebral tissue. You don't affect the deeper tissue. So for example, there's a big change in the correlation function at the short separation, that's shown here, but a much smaller change at the longer separation. And so you can use this information, you make basically correlation measurements at the short and long distance at two different pressures, and you can determine those constants, okay? And so once I have that constant, then I have it for that patient, all right, just by this pressure measurement. And I can measure the extracerebral tissue, the cerebral tissue blood flow changes, okay, during a perturbation. And so, for example, here is a measurement versus time of my cerebral tissue signal using different models, a semi-infinite long separation. This semi-infinite short isn't going to work. And this is the new model I've just been telling you about. And this is as a function of different pressures, probe pressure that I apply. And you can see what's really nice is that you get a really very flat signal of the cerebral tissue when you use this technique that I just told you about. Even more, you can go back to that finger tapping experiment. And there's like systematic variations that in the blood flow during these kind of tapping things that can be occurring in the scalp. And so if you look at this data, the only thing I want to alert you to is that this red curve is really the response of the cerebral tissue. And it's kind of like what you would expect. But if you were just using the other techniques, then you would not really get this shape as well, okay? And that's because there's systemic changes in the overlayer tissues, okay? So I just want to summarize that, again, you don't have to follow all the detail. If you're interested, you can read the papers. But basically, if you're interested in figuring out the changes in your cerebral blood flow, then you can do that fairly easily with these correlation techniques if you do this kind of pressure modulation. The other thing is that if you do the pressure modulation and you don't see a change in, if you don't see a change in your overlayers, this can be used as a check that your instrument's not working right. And so that's a kind of a really simple way to do it. There is another level of approach that people are taking now, and that is that they're sending in pulses, and they're doing diffusive wave, basically this diffuse correlation technique, the spectroscopy technique, but using it in a time-resolved way. So we'll see how well this works, but it's working at some level already. It's more complicated, but it's attractive because you can completely gate out the signals from your extracerebral tissues if you can make this work. So if you're interested about that, I can talk about that. Maybe David will talk about it. Okay. There's one more thing I wanted to tell you about technically, and that's what I call fast DCS. And so, you know, DCS is good. I've tried to tell you that it's good for measuring flow, but actually it can be noisy. There are all sorts of sources of noise, besides extracerebral versus not cerebral. And also, for example, even if you don't have to use it for brain, you could use it for muscle and look at muscle during exercise. But then actually there's motion artifacts, okay? If you have sort of static tissue that's moving relative to the detector, and that's going to give rise to decay in your autocorrelation function too. And so you want to, if you can, it'd be nice to get rid of these effects or figure out how to minimize them. And one way that you can do this is if you can make the measurement faster, okay? So what we did, well, I guess the key is that, so I've just sort of schematically drawn the correlation functions that we measure. And the main thing I want you to notice is that most of the information is in the beginning of it, okay? You really just want to know when did it start to decay. That gives you roughly the decay rate, okay? So there's lots of information at longer times, which isn't really we never even use it really, okay? Or we're fitting here, but it's not really that valuable, okay? And so there's a potential for data compression, okay? If we just want to take the data in the early stages. And so if you sort of think about that, and then you think about, and then computers have kept evolving and getting faster, and some of the electronics keeps getting faster. And so, for example, you can essentially now, before we would have a hardware device that would measure these correlation functions. But now you can just collect the photons. You know, you can digitize a photon arrived, make a TTL pulse, send it over to my computer, okay? And the computer can keep track of it, all right? So you can eliminate the correlator. You can do the correlation in the computer, all right? And so all of these improvements can let you make the measurements much faster. And so you can ask, well, why would I care about that, okay? And so here is, again, I showed you this measurement a long time ago where we had the cuff ischemia, right? So here we're not even doing the cuff. We're just putting the probes here. And I took the same photons, essentially, and made a measurement with the hardware correlators and the software correlators. Software is just doing it all on the computer by collecting those photon times. The red curve is the hardware, okay? So it's kind of here, and it's kind of noisy. Here's the software correlator. So, you know, when we first saw this, we thought, God darn, that's like really like a lot of systematics. But then if you looked at it really carefully, which I'm doing here, you can see that actually this is a real signal. And it's really the heartbeat signal, okay? And so we basically can resolve all this structure in the heartbeat. And so you can think about, you can make a measurement much, much faster. You can resolve these things. I'll say why this might be interesting in a second. But even you can think that if you can make the measurement this much faster, you can eliminate a lot of motion artifacts that could be occurring. Okay, so why is this interesting? One thing, so it's a kind of a new data type, okay, because we have a waveform, okay, of the flow. And so, for example, if you measure the flow and you measure the pressure waveforms, it's like measuring the current and the voltage waveforms in a circuit, right? And you can extract an impedance, right? And so you can look at these 1 Hertz fluctuations, and they're probing mostly the arterial responses, and we can basically get some new kind of information, okay? To me, that's one thing that's very exciting. New kind of information about the vasculature. But also, you have other things where you're basically getting rid of motional artifacts. There's often quite a lot of aliasing effects, okay? Typically, these measurements, we'd make them on a 1 second scale or a couple second scale, and there could be aliasing effects with the heartbeat. So those are gone if you measure it at 20 Hertz or 50 Hertz. So let me just say something about this waveform a little more, okay? So, because we've been working on this, right? So we can measure the flow here in the brain, and we can measure with the phenopress, we can measure the arterial blood pressure. And you'll notice even there's a phase shift between them, right? And so by looking at the amplitude difference and the phase shift, we can learn something about the impedance, okay? And so you can think of I've kind of told you to think about the vasculature as a resistor that's just changing. But actually, it's not just a resistor. And the next most complicated model is to make it an RC circuit, okay? It's called the Win-Kessel model. And basically, the main thing is that if you have an RC circuit, then it is useful to get this phase, okay? And if you get the phase and the amplitude, then you can really extract some meaningful numbers about the system. And again, I don't have time to go into it because I'm basically out of time, but basically you can measure what's called the critical closing pressure, okay? So there's a pressure, and again, there's a pressure driving the flow through your cerebral vasculature, But if for some reason the pressure got too low, then the flow would stop and the vasculature would collapse, okay? That's called the critical closing pressure where that occurs. Maybe that's of order 15 millimeters or something of mercury. But that could be a useful information to have about the vasculature, about the health of the vasculature, for example. And so it turns out we can measure this using this technique of the waveform analysis. And I'll just, again, I'll just summarizing it here. So you measure, again, the pressure waveform, you measure the flow waveform. This is the Fourier transform of those things. You can use the signal at 1 hertz. So at the 1 hertz, there's a change in the amplitude, or a ratio of the amplitudes, and there's a phase shift that you can measure. And you can extract some kind of a time constant, and we can think about what that means. And you can extract a critical closing pressure. And so this is something that we've been able to do in healthy subjects so far. And we think that it could be useful. Okay, so I think I'm just going to stop there. I mean, there's a few other things that I could say, but I think maybe that's a good point to stop. All right, so thank you.